Hello everyone and welcome to our channel Mootechie. It's wonderful to have you with us as we dive into a fascinating and essential topic, the world of welding. Whether you're new to this or just looking to refresh your knowledge, we're going to explore everything from the basic principles to the specific tools and techniques. So let's get started. Now let's begin with our introduction. Welding. Welding is the process of joining similar metals. This is done by the application of heat, with or without the application of pressure, and sometimes with the addition of a filler material. Moving forward, we see that welding methods may be broadly classified into two general groups. The first is plastic welding. This is also known as pressure welding. Here, metal pieces to be joined are heated to a plastic state and then forged together by external pressure, generally without the addition of filler material. The second type is fusion welding. This is known as non-pressure welding. The material at the joint, along with the filler metal, is heated to a molten state and allowed to solidify. And yes, filler metal is used here. Now let's explore plastic welding in a bit more detail. Some examples include A. Forge welding, which involves heating by a forge. B. Resistance welding, heating by electrical resistance. And C. Thermite welding, which uses heating by a chemical reaction and is done without filler metal. Coming up next, let's look at fusion welding. The common types are A. Arc welding, which uses heating by an electrical arc. B. Gas welding, heating by gases. And C. Thermite welding, which in this context uses heating by a chemical reaction and involves filler metal. Now let's understand one of the most important methods, electric arc welding. So what is an electric arc? An electric arc is produced when two current-carrying conductors are brought together and then separated by a small distance, provided there is sufficient voltage available to force a flow of current through the air gap. The arc produced is associated with a bright glow and intense heat throughout its length, and it can reach an incredible temperature of about 5000 degrees Celsius to 5500 degrees Celsius. That's unbelievably hot. Here's an interesting point about the voltages involved. An arc is produced between a workpiece and a carbon electrode at a voltage of about 35 to 40 volts. Meanwhile, the arc between a workpiece and a metal electrode happens at about 15 to 40 volts. The diagram on this slide illustrates the setup. It shows a high voltage, low amperage input going into a transformer. We see an electrode labeled A, and the output from the transformer becomes high amperage, low voltage current. This current flows through the electrode, creates an arc to the metal table where the workpiece is placed, completing the circuit for electric arc welding. So how do we create this arc? An arc suitable for welding may be struck in any one of the following ways. Between a consumable metal electrode and the workpiece. Between a non-consumable electrode and the workpiece. Between two non-consumable electrodes. Or between two workpieces themselves. Now, let's get to know the heart of the process, the arc welding electrode. We have two main families, consumable and non-consumable electrodes. First, the consumable electrode. A consumable electrode itself melts down during welding and subsequently deposits onto the weld bead. So the electrode acts as the filler metal, meaning no additional filler is supplied. The electrode material is chosen based on the base material considering chemical compatibility. Because filler is applied inherently, this type of electrode does not allow the autogenous mode of welding. Common processes that use consumable electrodes include SMAW, GMAW, GMAW, SSOW, ESW, SOW, ESW, and EGW. Now the non-consumable electrode. This one does not melt down or deposit on the weld bead. It remains intact throughout the welding, so filler is required to be supplied separately. The electrode material is independent of the base metal, but chemical compatibility must exist between the filler and base metals. This type allows all three modes of welding: autogeneous, homogeneous, and heterogeneous. Examples of processes using non-consumable electrodes are GTAW, also known as TIG, AHW, and CAW. This leads us perfectly to a deeper look at the types of welding based on filler material. First, welding with filler. This can be homogeneous, where the chemical composition of the filler material is similar to that of the parent materials to be welded. Or, it can be heterogeneous, where the chemical composition of the filler material differs substantially from that of the parent materials. This is also used for dissimilar material joining. And finally, welding without filler, or, which is called autogenous welding. Here, no filler is supplied for welding. Let's take a quick moment to expand on all those abbreviations we just mentioned. FCAW, flux core arc welding. SMAW, shielded metal arc welding. GMAW, gas metal arc welding. SAW, submerged arc welding. ESW, electroslag welding. EGW, electrogas welding. GTAW, gas tungsten arc welding. AHW, atomic hydrogen welding. CAW, carbon arc welding. Here's a key concept that brings it all together. An arc between a consumable filler metal electrode and the workpiece is extensively used in many of the welding processes today. When the arc with its intense heat is produced, it quickly melts the workpiece metal under the arc and produces a pool of molten metal. Simultaneously, the end of the electrode melts, and this molten metal is carried by the arc into the metal pool on the workpiece to provide the filler for the joint. You might also hear some other common names. For instance, gas metal arc welding, or GMA, was earlier known as metal inert gas welding, or MEG. And gas tungsten arc welding is often called tungsten inert gas welding, or TIG. Both of these use inert gases for shielding and are also widely used. Now, what equipment do you need for arc welding? Let's run through the list. 1. An AC or DC welding machine. 2. The electrode. 3. An electrode holder. 4. Cables and cable connections. 5. A chipping hammer. 6. Earthing clamps. 7. A wire brush. 8. A helmet. 9. Safety goggles. 10. And of course, hand gloves. Let's talk about the power source. An arc suitable for welding can be made with either an AC or a DC source. The voltage ranges from 15 to 45 volts depending on the process, and the current can range from 30 to 600 amperes, depending on the process and the material thickness. A DC arc is more stable because of the unidirectional flow of current and finds specific applications in cast iron and non-ferrous welding. On the other hand, AC welding has the obvious advantage of lower power cost, low equipment cost, and easy maintenance due to the absence of moving parts. Because of this, AC welding is becoming more and more common. To make this clearer, let's look at a direct comparison between AC and DC arc welding. In AC arc welding, the transformer has no moving parts and is simpler. It costs less and its maintenance cost is low. Since the distribution of heat is equal, there is no need for changing polarity. Hence, only ferrous metals are usually welded by AC. However, all types of electrodes cannot be used because the current constantly reverses. Only coated electrodes can be used. The problem of arc blow does not arise, as it's easy to control. But it can be used only when AC supply from the mains is available. And it's important to know that AC is considered more dangerous. Now for DC welding. The generator has rotating parts and is more complicated. It costs more and its maintenance cost is high. Heat distribution is different in the two poles, with about 2/3 in the positive and 1/3 in the negative. By changing the polarity, all types of metals can be welded. All types of electrodes, bare or coated, can be used. In DC, the arc blow is severe and cannot be controlled easily. But in the absence of an AC main supply, an engine-driven DC generator set can be used. And DC is comparatively less dangerous. So what exactly is this electrode? It is a filler metal in the form of a wire or rod, used as a terminal in an electric circuit for the purpose of producing an electric arc. We classify them as consumable or non-consumable. A consumable electrode is similar in composition to the metal being welded, and it melts to become a part of the weld. A non-consumable electrode may be made of carbon, graphite, or tungsten, which do not consume during the welding operation. Most electrodes you'll see are coated. When the core of the bare metallic wire is provided with a covering or coating of some fluxing materials, it is known as a coated electrode. The slag-forming constituents are silicates, manganese oxide, and iron oxide. The advantages are fantastic. It helps establish and maintain the arc. It protects the molten metal from oxygen and nitrogen in the air by producing a shield of gas. It forms a slag to protect the weld from rapid cooling, and it provides a means of introducing alloying elements. These coated electrodes may be light coated or heavy coated. Both bare and coated electrodes for hand arc welding are made up to 12 mm in diameter and 450 mm long. Now, let's look at some of the tools. First, the chipping hammer. A chipping hammer is used for removing slag and spatter from the weld. It's highly advisable to wear chipping goggles while using it so that flying particles of slag don't strike your eyes. The image on the slide shows a typical chipping hammer, which has a pointed end for chipping and a brush-like end for clearing debris. Next, the wire brush. This is a simple but essential cleaning tool. It's removing loose slag, spatter, and oxides from the welded surface after chipping. Safety is paramount, so let's talk about the helmet. A helmet is used by the welder for protection of his eyes, face, and throat from the harmful rays of the electric arc and from hot flying particles or spatter. Along with the helmet, specific goggles for welding are also used, especially during gas welding or cutting, or while chipping, to protect the eyes from bright light, heat, and debris. And we can't forget hand gloves. For protection of wrists and hands, gloves are worn by welders. They are made of leather or asbestos and should be as flexible as possible. Gloves provide protection against heat, sparks, and sharp edges. Now, what are we actually joining? Let's look at the types of welded joints. The common joints used in fusion welding are illustrated on this slide. We have several basic types. Butt welds, which can be a single V, double V, single U, or double U. T-welds, which can be single bevel, double bevel, single J, or double J. And we also have corner welds, lap welds, and edge welds. Let's explore each of these a little more. First, the lap joint. This is used to join two overlapping plates so that the edge of each plate is welded to the other. You simply overlap the plates and then weld the edges. These joints are typically used on plates having a thickness of less than 3 mm. Next, the corner joint. This is used to join the edges of two plates whose surfaces are at right angles to each other. The joint is made by joining the edges where the surfaces meet at approximately 90 degrees. It's used for both light and heavy gauge sheet metal. Interestingly, in some cases, a corner joint can be welded without any filler metal, just by melting off the edges of the parent metal. Now, the butt joint. This is a very common joint, obtained by welding the ends or edges of two plates which are approximately in the same plane. In butt welds, the plate edges do not require beveling if the thickness is less than 5 mm. If the plate thickness is between 5 mm and 12.5 mm, the edges should be beveled to a V or U groove. And for plates thicker than 12.5 mm, you should have a V or U groove on both sides. Another important one is the T-joint. The T-joint is obtained by joining two plates whose surfaces are approximately at right angles to each other, forming a T shape. It's widely used to weld stiffeners in aircraft and other thin-walled structures. These joints are suitable for materials up to 3 mm in thickness. Finally, the edge joint. This consists of joining the edge of parallel plates by means of a weld. It's obtained by joining two parallel plates together at their edges. It's economical for plates less than 6 mm thick. However, this joint is unsuitable for members subjected to direct tension or bending, as it's not very strong. The position you weld in is also crucial. Welding positions are classified as follows. The flat position, where the filler metal is deposited from the upper side of the joint with the face of the weld horizontal. The horizontal position, where the weld is deposited upon the side of a horizontal surface and against a vertical surface. The vertical position, where the line of welding is in a vertical plane and the weld is deposited upon a vertical surface. And the overhead position, where the weld is deposited from the underside of the joint. It's the reverse of flat welding and is the most challenging position. Now let's shift gears and talk about resistance welding. In resistance welding, the metal parts are heated to a plastic state over a limited area by their resistance to the flow of an electric current, and then mechanical pressure is used to complete the weld. Here, two copper electrodes are incorporated in a circuit of low resistance, and the metals to be welded are pressed between them. The circuit is completed, and because the electrical resistance at the joint is so high compared to the rest of the circuit, if the current is heavy enough, the highest temperature is produced right at the joint we want to weld. The diagram shows the electric circuit of a resistance welder. We see a movable arm and a fixed arm, each with a water-cooled electrode. The workpiece is placed between them. Pressure is applied and the circuit is connected through a regulator and a transformer to an AC current supply. Resistance welding is used with sheet metal from 0.5 to 3.2 mm thick and with steel pipe tubing, and it's employed mainly for mass production. Metals of medium and high resistance like steel, stainless steel, monometal, and silicon bronze are easy to weld this way. Another major category is gas welding. In gas welding, the heat required for heating and melting the parent and filler metals is obtained by the combustion of a fuel gas with oxygen. The fuel gases used are acetylene, hydrogen, and natural gas. Acetylene is the most widely used because the temperatures from its combustion are much higher than those from hydrogen or natural gas. However, an oxy-hydrogen flame may be used for welding thin sheets of steel and low-temperature melting materials and alloys. So where do these gases come from? Let's discuss the supply of oxygen and acetylene. Oxygen is produced industrially by electrolysis of water or by liquefaction of air and separating the oxygen. The gas is then compressed and charged into cylinders, typically with a 40-liter capacity, to a pressure of about 15.4 megapascals. Commercial acetylene is produced by the action of water on calcium carbide. Storing acetylene at high pressure is tricky, so it's dissolved in acetone inside a cylinder. The steel cylinder is first packed with about 80% porous material like asbestos or charcoal. Acetylene cylinders contain 1.7 to 9 cubic meters of free acetylene at a pressure of 1.7 megapascals. The heart of gas welding is the oxy-acetylene flame. This flame is produced when the two gases meet and undergo combustion, evolving heat and light. With commercially pure oxygen and acetylene, it produces the hottest known flame with an estimated temperature around 3,500 degrees Celsius. The actual temperature depends on the ratio of fuel gas to oxygen. And since temperature isn't the only requirement, varying ratios are used for different applications. These flames can be classified into three categories. 1. The balanced or neutral flame. 2. The reducing or carburizing flame. 3. And the oxidizing flame. Let's describe each one. First, the neutral flame. The neutral flame is produced by burning a 1-to-1 mixture of oxygen and acetylene. This flame is characterized by a well-defined luminous inner cone, gradually rounding off into an outer envelope. The intermediate zone is slightly reducing and is hard to distinguish. Welding is done using the flame in this zone. The outer envelope is neutral and provides a protective atmosphere. This is the most generally used flame for all heating and welding applications. The diagram indicates temperatures. The inner cone is at about 2100 degrees Celsius, and the outer envelope is around 1260 degrees Celsius. Next, the oxidizing flame. This flame is produced by burning acetylene with an excess of oxygen. The inner cone becomes short and pointed, and the envelope is shortened and blue in color. This flame is used as a preheating flame in cutting operations and in the fusion welding of non-ferrous metals like brass and bronze. Its intense heat also compensates for the high heat loss in conductive metals. The image shows a flame with a small narrow outer envelope and a sharp defined inner cone. And finally, the reducing or carburizing flame. This flame is obtained by burning an excess amount of acetylene. It has a distinctive secondary luminous zone called an acetylene feather surrounding the inner cone. The outer envelope often has a reddish tinge and may carry some soot. It's used in welding metals like nickel, alloy steels, and non-ferrous hard surface materials. Its carburizing nature can even be used to advantage when welding low-carbon steels to increase the welding rate. The illustration points out the acetylene feather, the bright luminous inner cone, and the blue outer envelope. Flame temperature is a critical characteristic. Higher temperature means more efficient heating and melting. The temperature isn't constant, it varies along and across the flame. It depends on the oxygen to acetylene ratio, and increases with this ratio up to a point. The maximum temperature in a reducing flame is about 2900 degrees Celsius, in a neutral flame it's about 3250 degrees Celsius, and for an oxidizing flame it can reach about 3500 degrees Celsius. So what equipment do you need for oxy-acetylene welding? The setup consists of a welding torch with a set of tips, hoses, pressure regulators, cylinders for oxygen and acetylene, and accessories like goggles, a friction lighter, and gloves. It's often mounted on a trolley to make it portable. The diagram labels all the parts: the torch tip, mixing chamber, needle valves for acetylene and oxygen, the hoses, the pressure regulators with their cylinder and working pressure gauges, and the gas cylinders. Let's look at the welding torch itself. The torch is the device used for mixing the two gases in the right proportions, burning the mixture at the tip, and directing the flame. It has a handle with inlet connections and control valves for the gases. At the other end is the mixing chamber and the tip. The flame is produced by lighting the mixture at the torch tip. The tips are made of a non-ferrous metal like copper because of its high thermal conductivity, which helps keep the tip cool. Larger tip sizes are used for thicker pieces of metal because they release more gas and produce more heat. Pressure regulators are vital for safety and control. Their function is to reduce the high cylinder pressure down to a safe desired working pressure, and to maintain that constant working pressure regardless of changes in the cylinder pressure. You'll see two pressure gauges on each regulator. One shows the pressure left in the cylinder and the other shows the pressure being delivered to the torch. The hoses that carry these gases need to be strong, non-porous, flexible, and light. Reinforced rubber hoses made specifically for this purpose are used. And it's absolutely critical that the hoses are not interchanged between the gases. This brings us to a very important topic: color code and safety. To prevent dangerous mix-ups, a strict color code is used. Green or black color is used for oxygen cylinders, hoses, and knobs on torches. Maroon or red is used for acetylene cylinders, hoses, and knobs. Furthermore, all oxygen connections have right-hand threads, and acetylene connections have left-hand threads. This system allows for proper identification and avoids the potentially catastrophic consequences of connecting the wrong gas to the wrong system. We also have welding rods, which are the filler metals. The properties and composition of a weld should match the base metal closely, which is why many different types of welding rods exist. They are produced in diameters from 1.5 mm to 10 mm and in a standard length of about 1 meter. Finally, let's discuss oxy-acetylene welding techniques. You start a weld by preheating the base metal to produce a small puddle of molten metal. In forehand welding, the rod leads the torch in the direction of travel. The flame is directed forward. This produces neat welds and is used for thin sheets up to 4 mm thick. For a right-handed welder, this is a leftwards motion, so it's also called leftward or forward welding. In backhand welding, the torch leads the rod. The flame is directed back at the molten puddle and the completed weld. This is extremely helpful for vertical or overhead welding, as it helps control the molten metal. It also concentrates more heat, making it suitable for thicker workpieces. For a right-hander, this is a rightwards motion, hence it's called rightward or backward welding, often used in pipe and plate welding. And as a quick related process, we have the gas cutting process, which uses a similar setup but with a different torch to cut through metal. Thank you for joining us on this comprehensive journey through the fundamentals of welding. We hope you found it insightful and inspiring. Thank you. See you in the next class.